Determination of soil crop suitability for Enugu State using Geographic Information System (GIS) and Multi-Criteria Evaluation (MCE). Abstract: the study was targeted at developing soil crop suitability map for Enugu State through Geographic Information System (GIS) and Multi-Criteria Evaluation (MCE). This suitability mapping carried out with the help of GIS was reviewed side by side with the prevailing land use (LU) practice of the region. The research analyzed prerequisite to achieving optimum utilization of the available land resources in Enugu State, Nigeria. Standard relevant land characteristics, LCS, quality, Q, alongside that of climate, topography and soil based on medium-intensity survey techniques were collected, analyzed, and the result was held after converting the data into a usable format for evaluation, process. Land mapping units, LMUs, were assigned to each location through an intensive querying analysis. The current land use land map of the study location was produced, and a clear inverse relationship between suitability map for selected crop types and current vegetation analyzed. The result shows that out of the 7,161 square kilometers, about 28.06% was highly suitable, S1, 22.66% moderately suitable, S2, 14.51% marginally, S3, suitable, while 7.69% not suitable, N, for rice production. Secondly, 25.93% was rated as highly suitable, S1, 17.47% moderately suitable, S2, 26.04% marginally suitable, S3, while 3.49% as not suitable, N, for maize crop. Thirdly, the result revealed that 29.26% was highly suitable, S1, 18.88% moderately suitable, S2, 16.77% marginally suitable, S3, and 16.77% not suitable, N, for cassava production. Overall, the results indicate that the study area has a varied huge potential for rice, maize, cassava production. The results can serve as guide to investors in prioritizing investment towards large-scale commercial production of rice, maize, cassava, etc. in Enugu State. Introduction. Geographic Information System, GIS, is a framework for gathering, managing, and analyzing spatial data which allows and enhances viewing, understanding, questioning, interpreting, and cross-analysis of data in many ways that previews patterns, interrelationships, in the form of maps and charts, etc. It answers questions and solves problems by looking at the data in a way that is quickly understood and easily shared. Basically, the input data for GIS are site-specific and are obtained through remote sensing, RS, the Global Positioning System, GPS, or ground surveying. Through the input of GIS, complicated analytical functions are simplified and the results presented visually as maps, tables, or graphs, allowing decision-makers to virtually see the issues before them and then select the best course of action. GIS is playing an increasing role in agricultural production throughout the world by helping farmers increase production, reduce costs, and manage their land more efficiently. Striking a balance between the inputs and outputs on a farm forms the basis to its success and profitability. The proficiency and capability of GIS to analyze and visualize agricultural environments as well as that of workflows has proved beneficial to the farming industry. GIS offers an agricultural system with the capacity to assemble, analyze, and apply relevant managerial variables such as meteorological, soil, yield, moisture data, etc., which serves as a practical planning aid. A closer involvement and integration of which ensures precise on-the-farm monitoring and control, to assist resource allocation and boost better returns. Crop yields can be maximized through integrated soil crop systematic planning, which considers basic decisions like crop selection, planting, sowing and nutrient management, etc. 1.2 Statement of problem. In many developing countries, there is a general paucity of land use information. There is little or no reliable soil/crop database to assist farmers towards optimal utilization of soil for agricultural production and systematic planning. The general knowledge of the in-depth richness of Nigerian agricultural soil alone has not helped to solve the escalating problem of food shortage. To increase the production of rice, maize, cassava etc., environmental factors must be favorable. This requires the introduction and inclusion simple technological inputs. The research is structured to shift away from the regular guesswork in agricultural planning to a system of precise identification of the most favorable or viable agricultural land of the study region in respect to rice, maize, and cassava production, and in addition, determine the percentage of the land that is most suited and what level of yields the farmers should anticipate in the varied land suitability. 1.3 Study Objective. The aim of this research is to develop a soil crop suitability of the study region through GIS and multi-criteria evaluation, MCE. The study will further 1. Determine the current land use profile of Enugu State. 2. Examine the level of suitability variations of the cardinal locations within study area, based on FAO standard, and 3. Produce a schematic and comparative review of study area to assist managers/farmers on key decisions where future inputs etc. should be required to improve crop production. Materials and method. 2.0 Location. Enugu State has an estimated total area of 7,161 square kilometers and is situated in the eastern part of Nigeria, 6°30 and 7°30 E. The study location shares common boundary with Abia, Imo, toward the south, Ebonyi State eastward, Benue State northeast, Kaji State, northwest and Anambra State west. 2.1 Climate. The soil status of the state is very good with compatible all-year-round climatic conditions. With an altitude of about 731.9 feet above sea level, the drainage system is fairly perfect during the rainy season. www.nowchilled.com.ng web link. The average temperature is about 87.16 degrees Fahrenheit, 30.64 degrees Celsius, usually in the hottest period of February months each year. The lowest, 15.86 degrees Celsius, temperature occurs in the month of November. The highest rainfall, which occurs in July, is about 35.7 cubic centimeters 2.18 cu, and its lowest is about 0.16 cubic centimeters 0.0098 cu in, which in most cases is observed within the month of February. www.nowchilled.com.ng web link. Study area location and climatic conditions. 2 parameters for suitability analysis. Identification of the basic requirements for rice, maize, and cassava growing areas were made possible through comparative review of various relevant literatures, FAO standards etc. and desk search of available data. The identified factors included climate, humidity, temperature, topography, slope, soil texture, soil pH, soil drainage. The complete methodology includes identification and grouping of the spatial characteristics of Enugu State, conversion of same details into digital format, deduction of various suitability analysis within the GIS environment, and further presentation of the outputs in a thematic map. Relevant soil data, properties, was obtained from NASTRA, 2013. The detail here shows the soil properties, both physical, chemical details etc. of the study location. 3 soil parameters, drainage, texture, and pH, obtained from an attribute table via ArcGIS 9.3 software. Subsequently, for each parameter, the thematic maps were developed. Accordingly, each map was georeferenced to the Universal Transverse Mercator, UTM, coordinate system. Through the software package, necessary information for the slope was deduced from Digital Elevation Model, DEM. The overall work plan, methodology for the research is illustrated in Figure 3.2 below. 2.3 Research Methodology Chart. Basically, the climate, local topography, soil texture, and existing vegetation etc., which are the main components of the environment, are key determinant assessment factors for land productivity. Analysis of suitability was carried out by cross-examination of the prevailing land use pattern, potential feasibility, and the economic viability. Acquisition of spatial data and rendering of same into map or pictorial format were carried out to accomplish desired relevant land resource management. Other inputs are here placed side by side, as land suitability cannot be solely based upon biophysical resource information. Relevant information such as transportation and demographic features were put into consideration. The surface and overlay analysis were processed using GIS and the various vast amount of spatial information effectively captured. 3.4 Data assembly. Data assembly and manipulations involves importation of shapefile of study region into the GIS environment. The assembled geographical data is processed after combination and transformation into relevant decision. This involves personal, expertise inputs or decision makers' preference as regards use of specified decision rules, manipulation of information, etc. For the spatial multi-criteria decision-making process, the input data is geographical as captured in rice, maize, and cassava. Suitability are deduced via the input of geographic data, physical and chemical properties of soil, topography, climate and land accessibility. Table 2.6 A data analysis. S/N. Data name. Procedures. Analysis. I. Nigeria SAT1 Imagery. Radiometric correction and geometric, clipping and classification. Extraction of Enugu shapefile, imagery of study area. 2. Shapefile of Enugu State. Importation into ArcGIS environment. Shapefile creation. 3. STRM. Creation, generation, of DEM, imagery. Extraction of shape and 4. Climatic data, rainfall, relative humidity and temperature. Creation of shape files, clipping of study area. Interpolation and reclassification. V. Geology map of Enugu State. Importation into ArcGIS environment. Digitization, reclassification and overlay. 6. Soil map of Enugu. Importation into ArcGIS environment. Digitization, reclassification, and overlay. 2.7 Extraction of the study area and agricultural land. The area of interest, AUI, study area was extracted by means of an on-screen digitization. This is accompanied by masking out those subset module of ENVI software, ver.4.7. In order to identify the cropland with highest and lowest rank of vigor, the Normalized Difference Vegetation Index, NDVI, which is an indicator assessment, was adopted. Further, the detail is incorporated with Decision Tree Classifier, DDC, and the agricultural land was successfully delineated from. This is consequently used for further analysis. The link roads, railways etc. were also put together in as shown in Figure 4.1. 2.8 Assigning weight of factors and multi-criteria evaluation, MCE. Factors established were the most relevant, and weighting analysis are done to express the relative worth, importance, of each factor to the other with respect to the degree of effect or impacts on crop growth rates, performance, and yield. Table 2.10 shows suitability levels for each of the factors which, as expressed, are used for the construction of criteria maps, one for each factor. Based on FAO Suitability Classification Standard, the suitability levels for each factor were ranked. These included: highly, most preferably, suitable S1, moderately, preferably, suitable S2, marginally, less preferably, suitable S3, and N not suitable etc. Table 2.10, the SADI rating scale. Intensity of. Definition. Importance. 1. 1:1, equal importance. 2 factors contribute equally to the objective, equal weight. 3. Somewhat more important, greater. Experience and judgment slightly favor one over the other. 5. Much more important. Experience and judgment strongly favor one over the other. 7. Very much more important. Experience and judgment very strongly favor one over the other. Its importance is demonstrated in practice. 9. Absolutely more important. The evidence favoring one over the other is of the highest possible validity. 2, 4, 6, 8. Intermediate values. When compromise is needed. Aggregate of the criteria. Weighted linear combination is the most commonly used decision rule. Formula: S equals .wi11x.cj. I. Where S is the composite suitability score. 11 factor scores, cells. Wi weights assigned to each factor. Cj constraints, or Boolean factors. Sum of weighted factors. Product of constraints: 1 suitable, 0 unsuitable. Table 2.14, pairwise comparison matrix of subcriteria with respect to soil. Soil pH. Soil texture. Soil. Nth root of. Eigenvector. Depth. Drainage. Product of values. Soil pH. 1. 1/3. 1/3. 1/3. 0.439. 0.093. Soil texture. 3. 1. 3. 3. 2.280. 0.480. Soil depth. 3. 1/3. 1. 1/2. 0.841. 0.177. Soil drainage. 3. 1/3. 2. 1. 1.189. 0.250. Sum. 4.749. 1. Max equals 4.214. CI equals 0.071. CR equals 0.08. Table 2.15, Spatial variation of slope. Suitability class. Slope, percent. Area, ha. Area, percent. S1. Equals 6. 861,250. 37.09. S2. 6 to 13. 452,352. 19.48. S3. 13 to 25. 354,201. 15.25. N. 25. 654,112. 28.17. Results and discussion. Figure S. 6, 7 and 8 SHOWS the thematic map of the crop, rice, maize and cassava, / soil suitability rating for the study region. The tables 4.1, 4.2 and 4.3 further present the varied suitability capabilities of the examined areas. Also, Figure 4a, 4b and 4c shows the pie chart of the result of the suitability dimensions for rice, maize, and cassava respectively. The agricultural land has been ranked as highly, most, suitable, moderately, appreciably, suitable, marginally, relatively less, suitable or not suitable, after cross-examination and analysis. Highly suitable area, with respect to rice, is characterized by well/moderately poorly drained soil, very deep/deep soil and loamy texture, while marginally suitable area is characterized by shallow soil and very clayey texture. Fig 4.0, Land Use Land Cover of Enugu State. On the other hand, the characteristics crop requirements for maize and cassava are presented in Table 10 and 11 respectively. Cross-matching of the each crop alongside the land units were done to arrive at the suitability classes. Through the principle of limiting conditions, the land was rated as marginally suited S3 for maize and cassava respectively. This is partly attributed to the high nutrients requirement of maize and other critical factors that affects maize production, especially that of moisture and drainage. Next in the ranking is the less suitable, moderately, suited, S2. The rating or grouping of the land was grossly affected by the nutrients requirements of each crop. The other portions were rated as highly, most, suited, S1, and not suitable, N, using the analytical approach respectively. 4.5 pedologic index for each crop within study area. S1, S2, S3, N. No. Data. Rice. 28.06%, 22.66%, 14.51%, 7.69%, 27.06%. Maize. 25.93%, 17.47%, 26.04%, 3.49%, 27.06%. Cassava. 29.62%, 18.88%, 16.77%, 16.77%, 27.45%. Table 4.5 Soils/crop suitability ratings for Enugu State. The suitability ratings reveal that the zones which are highly suitable and moderately suitable for rice farming fall into the key LGA, Uzuwani, Ikagwu, Aji River, Ananri, Nganu East, and Isihuzo, which are the principal areas of agricultural produce in the state. The outstanding performances of FATIMA projects within the state also attest to the potential status of the region's viability. Based on the varied soil and environmental status, the suitability classifications for maize and cassava as indicated on the table above. 4.6 Limitations. The use of GIS is based on facts and figures geographic information. Availability of the needed data and the cost of acquisition remains one of the salient challenges. Footing the bill to collect new data and to convert paper maps and data into digital format continues to be a problem. In many cases digital data do exist, but there are issues of confidentiality, national security, etc. There is no clearly defined community and LGA boundary delineation for the study area. Most of the boundary reference points are either linked to a river course, hills, or other demographic features. These made it difficult to ascertain the precise size of key and notable zones and areas of interest. Conclusion. GIS analysis and spatial modeling offers one of the best planning aids for precision farming. As seen from the results, it makes it reliably efficient to analyze land capability or potential with higher accuracy. The result shows, at a glance, what to expect from where and how by ensuring judicious use and allocation of resources for optimum yield. This work shows that the inclusion of GIS in pre-farming activities is an effective tool for cost-effective projection when it comes to feasibility and productivity analysis. It helps to preview the results of the integral combinations of key factors of crop production to highlight most suited zone, areas, for commercial output of various crops. The results of this work should serve as guides to investors in prioritizing investment towards large-scale commercial production of rice, maize, cassava etc. in Enugu State. Contribution to knowledge. Apart from boosting the confidence of agricultural investors, GIS simplifies farm input return analysis and guarantees justifiable allocation of resources. This research work directs focus on the indispensable need for inclusion of technological aids in today's agricultural practice which has not been given due attention. In summary, this work has simplified the answer to where is most suitable or less suitable for crop production across the study region. Recommendations. While the result of this research reflects the real status of the varied crop production capability of Enugu State, I recommend it as guides in agricultural planning and investments. Secondly, further work should be done on accurate boundary delineation to reflect the sizes of each community and LGA across the states in Nigeria. Finally, the government should give attention to creation of agricultural database and encourage the use and inclusion of GIS in the industry. Acknowledgement. We wish to acknowledge the roles of the Advanced Space Technology and Applications Laboratory UYO, ASTL, and Dr. Amodu Usimian for the encouragement and supports without which this work would have been impossible.